Now we
Oh, mine
start
away
now,
here?
he's here.
We're gonna get top of your
All
head.
right, so tonight, we have a special guest speaker from KU. Dhwani. Vani is a aspiring astrogeologist with a passion for exploring connections between astronomy and geology. I think she'll probably cover a little bit of that in her talk tonight. She's currently an undergraduate research assistant at KU, pursuing a degree in astronomy and I think geology,
Yep.
both. She's also a senior member of the UN Women 30 for 2030, which is a group for, trying to get equality for women, some social justice issues, some sustainability things.
Education in STEM.
Yeah,
In
education.
Asia, in Asia specific regions.
So anyway, Jennifer suggested that or contacted Dhwani, or Dhwani talked to her, I'm not sure how that worked, but we were able to get her set up for tonight's presentation, so I'll turn the floor over to you.
Hello. Hope you all are doing good. There's a lot of stuff on here. I'm gonna try to simplify. But if you all have any questions about anything, feel free to stop me in the middle so I can explain better with visuals. And yeah, I'm going to be talking about Raman spectroscopy and covering research in the world of astrobiology as a whole. And the research I'm currently doing with both my research professors in the university. A lot of people try to understand what astrobiology is. And there are many different definitions out there on what it actually is. And there are so many papers that are like, we have life on Venus, we have life on Mars, but how do we actually go about confirming the same? And what life actually means and what biosignatures mean is something I'm going to start with. So any form of life may be, it leaves some sort of chemical, biological signature behind, may it be in rocks, in chemical forms, over billions of years. We have seen them as fossils, and many of them we have found in the planet Earth itself. And Earth as a rock is like a history book because of how much data it gives us of the previous different decades that have gone by. And it holds signatures of life, microbial may it be, or as big as dinosaurs and mammoths. And that's why my research in Raman spectroscopy basically connects Earth's clues with the type of detection that's been happening using perseverance and the sort of machines it has, and how I'm able to connect both of them to understand what biosignatures are and how you do research on them. There are many types of biosignatures to the point that we still keep finding new different various ways to explain what a biosignature is. The main ones are chemical and mineralogical and structural. These all are based on chemical compounds or structures left behind in rocks. We have seen a lot of them in different bands, and that's when we see methane in the atmosphere and we are like, oh, it may be a biosignature. Now, biosignatures also are defined in three main categories other than the detections, and that is ambiguous biosignature, in which place we are not sure it is formed because of biological means, biogenetic signatures, and abiotic signatures. Abiotic signatures is it's formed because of some process that happened on a planet like Earth, and the atmosphere created it because of volcanism and stuff like that, and the chemical composition that a life should give was detected, but it was not formed because of life itself. And that's what an abiotic signature is. And it's pretty important to understand. Oh shit. Sorry. Didn't mean for that to happen. It's pretty important to understand the differentiation of these three, because we read a lot of research papers and the news that says, oh, we detected life on Mars, we detected life or biosignatures in the atmosphere of Venus. But when you go in detail, a lot of these are either abiotic or ambiguous signatures, which means we are not sure if it's biotic or not. We don't know if it has been formed because of biological processes, and that's why it's very important to know. I should have had this slide up. But yeah, those are in official terms of the definition of biogenetic feature and an abiotic feature. Astrobiologists, this is the hardest part they do of their job, is to figure out what kind of signature is formed. Because most of the time, it's abiotic. It's pretty hard to find life in Earth and like pre-existing ancient Earth and life found on different planets. Why rocks matter and why geology is important in astrobiology is something I have had the pleasure of researching. It's basically, as I said, that Earth is like a history book that has a lot of data and a lot of records. It holds a lot of, I guess, signatures of life that has gone through different geological decades and spans of time. And you see them reflected when you take a slab of rock that has gone through a lot of these processes, such as this is a part of rock that I am researching under Raman spectroscopy, and you see that there are different structures in there which it's hard for them to be formed without any biotic activity, and so we were able to find them because of we think they are because of microbial proof of life from a period on Earth. And when we do Raman spectroscopy, we basically compare chemically, structurally, and using specific rays and radiations to figure out what sort of detection and what chemical composition and structure do the same have, to be able to decide if they are an ambiguous signature, a biotic signature, or an abiotic signature. Should not move that. That's the rock I am doing my research on. As an undergrad, I have a lot of access to different equipment and I get to play around with them and learn different things from different ways. And it is a sample that my professor found from Australia that has different laminated structures, and there is a thing called oolitic and stromatolitic structures, which are basically identification found in rocks, where you can be like, oh, that was formed because of something biotic. Like that's the first guess, but there are so many things that can form different effects in a rock, like weather processes, weathering and stuff. So to be able to differentiate them, we do stuff like Raman spectrometry. Sorry, I don't know why that keeps happening. Just an understanding of what Raman spectroscopy is. It is a way to detect the different organic and mineral compounds of a rock. That is the Raman spectroscopy device back in the Department of Geology that I've been using to do my research. And it is very important to figure out if what type of signals that we get back, because it's basically we shoot different bands at the rock or the sample we have, and we get data back, spectrometry data. The same happens on some of the satellites present, and to be able to decode the data and understand if it was caused because of physical life processes or because of abiotic processes is when you look at different fields. I am not even touching this. As I said, it is really moving. It should detect it now. Okay. Yeah. By the way, for those who need a bit clarification of what Raman spectrometry is, we are shooting different kinds of lasers of different intensities. Yeah, and detecting the scattered light is basically like a molecular fingerprint of different structures that are the atomic structures, and what composition does the same have at a very core level. And to be able to detect and understand that in different things is what we do. That's a picture, that's an artist's illustration of what ancient Mars would look like. And as we know that Mars is a very iron-rich planet, a lot of its soil has always had a lot of iron content, and so that's why when, as a geology major, when I'm getting to choose a rock sample to compare these processes with, I look for caves based in low light environments because as it's further away than Earth is, and basically environments where there is higher number of iron presence and magnesium presence to replicate the regolith environment that is found in Mars and would have been found in early Mars. And these sort of, when I do find a sample from a place that has a fruit textile, like the A16 sample that I'm studying, it's easy to compare them because those are the type of rocks that would be found on Mars, on early Mars. And as we send rovers, as we send different technologies to study the surface of Mars, to study the composition of Mars, what we are basically going to find is these kind of rocks. And if these kind of rocks can hold microbial life signatures, so if there was life on Mars, it would be able to show us the same thing. And so we can compare both the study and be like, the same rock, in nearly approximately, if we assume the conditions of ancient Mars, this would be what it would give us. And to be able to compare and analyze the same is what my research mainly does and what I'm trying to do. For those of you who know Perseverance, the rover that is currently doing studies on Mars, it has a Raman spectrometer called Sherlock, which has a tiny camera that is called Watson, which I think is really cute because Sherlock and Watson. And what it basically does is, as you can see, I've sort of explained in detail what the Raman spectrometer does, but basically whatever I'm trying to do on Earth, collecting data, imaging, shooting the lasers at it and collecting that scattered light and being able to analyze that and forming like a mineral face map, which basically means what sort of minerals are located in the captured image or in the structure, is what that's doing on Mars. And that data is open to the public. So you can go have fun with it, compare your research with it. Proxy is a word which we basically use scientifically to compare different environments. Earth as a proxy for Mars is, as I said, that we are looking at specific areas on Earth that can replicate what we assume was ancient Martian life. This is a mineral composition map. This picture is an image that I took from a Harvard research study trying to understand the data we are getting back. And they have made a mineral composition map which shows the silicates, the carbons, and the different phosphates that are found in these, I guess, areas where the rover is looking for. And when we do the same, the Raman maps show different, like which areas would be higher, like highly preferable for biosignature to be found based on what all research that has been done on Earth, and to be able to compare them is what we are trying to work on. My laptop's still on the first slide, by the way. I have no idea why. This is my log sample. That's A16. As you can see, that number 3, the circle, is the structure I talked about. A little bit of geology on how we do sample prep, cutting it, polishing it, making thin sections of it, and that is it under the Raman spectrometer, getting ready to take spectral lines from and being able to do the peak fitting to find out what actually is the composition of the specific areas where we assume they may have fruit textiles. Fruit textiles is, in the most basic terms, I can describe that as microbial life presence, and that's how we do research and by comparing them with other spectral analysis done and being able to be like, okay, that's definitely formed because of biotic reasons and it's a chemical biosignature. As you can see, number 3 is like a structural biosignature, because that structure, it would have only been able to form if there was like an air pocket and microbial life living on it, and after that dying. So it develops in different ways. That is an example of what a spectral signature looks like. I took that, by the way. It is one of my first good signatures. Hematite is a type of rock composition that is really known to be very instrumental and important if you want to look for life, especially microbial life, because we have come to the conclusion, at least in some part of the scientific community, that if you're going to find life, it's not going to be intelligent, or it would have found us already. So it's going to be at a microbial, microscopic level. It's not going to be something so big, or we would have already been able to detect it. So to be able to do research and draw interpretation of such type of, I guess, Raman targets, and comparing them with what we find in Mars, or where we find as data we get back from Venus, and to be able to compare the same, and if they do match, we say that the spectral signatures prove that this was formed because of biogenetic reasons, and so there was life, or it was formed because of reasons of life. There are a lot of questions in astrobiology we still don't know, to the point that astrobiology itself is still being defined as a whole group of study. And some of the open questions that I found that I constantly have to face and try to work my way around are how do we remotely, without actually seeing a sample, without actually having it in a lab environment where we can do so many different kind of tests that would be hard to wait and send another rover and do testing for. We still are trying to figure out what is the threshold to define 100% of biogeneticity, which is the different kind of biotic lives, and how we can integrate different subjects, like geology, chemistry, and biology in space missions to get a complete idea of what else is out there. Yeah, that's my 2 research professors that I'm working with. Professor Claire Marshall is from the Geology department, and Professor Allison is from the Astronomy department. I do research under both of them, and they have helped me get and do as much research as I have done, and I'm planning on doing the same as I graduate from university. Thank you.
Have you been able to, or is anyone doing this technique on, as you said, being remote, having the equipment, the rovers and everything on Mars and not in a lab where you can access the samples and everything? Has anyone tried to use meteorites as a way of trying to find out what's out there that they can actually hold in their hands in a laboratory?
That is true, and they have done a lot of research, including Raman spectrometry research, on different meteorites and all. The issue is the sample size is not as big as we hope for, because seeing something in your meteorite form, it needs to be at a very small scale, whereas if you look at a whole planet, it's a bigger scope of, like, I'm not gonna lie, from a perspective of somebody who is learning about all of this, I'm still new and I do not know everything, but it's hard for me to see if it might be easier to detect life in terms of like biosignatures and all in a sustained environment like a planet than a meteorite, because there is so much emission happening, there is so many other things happening. But I do know that research has been done on some of them. In fact, the Spencer History Museum has a meteorite sample that was given to the university, and you can go and like check it out there, and you can take a hand lens, which is like a geology fancy magnifying glass, and you can look at it under UV light and different kind of light, and you kind of see the interaction is a little different. We don't need that anymore. It's fine. But yeah, I do not know all the research that has been done. I was curious about it at some point. And if you like look up a couple research papers, I'm sure you will find a more concrete answer that's better than what I'm trying to give.
Follow up on that, could the heat of entry cause validity questions on the biosignatures on the meteorites?
There is something called diagenesis, and if my understanding is correct, because of difference, like this happens even in planet Earth, like the composition of rock changes on what it is formed because of spikes in temperature or in pressure, and these lead to different kind of structures being formed. And I don't know how in a meteorite you'll be able to distinguish both of them if you had to really look to see if it was, I guess, formed because of reasons of biology. Because that temperature and pressure will cause difference in rock crystallization and how and what chemical composition is present.
Yeah, because I would wonder if the intense heat could affect the chemistry.
I know it might not affect on a very molecular atomic level, but overall the type, I do know at least that happens on Earth, so I wouldn't be surprised if that happened on like meteorites and stuff. Because hydrothermal zones and all, they do have a different, I get rock formation like structural wise and chemical wise, that there is a peak sort of temperature gradient, like above this, those sort of rocks can't be formed, but they can be like changed into forming another sort of rock,
Right.
which is different molecular structures, especially high peak temperatures. Because of volcanism, a lot of rock composition chemically changes. So yeah, maybe.
I think the biggest concern that they have with meteorites isn't so much the entry, the atmospheric entry, because that only affects they're only burning in the atmosphere for a couple of seconds. And they were basically absolute zero or close to it when they hit the atmosphere. So everything in the interior, it's just a very thin layer on the outside. The biggest concern I think they have is trying to determine if someone finds a meteorite laying on the ground on Earth, how much contamination, because it is a rock. And there's no erosion and rust and water and all that other stuff when it's flying around in space. But once it gets on Earth, it rains and, big changes in temperature. And I think that's why they wanted to bring all those samples back from the asteroids to get pristine samples
Right.
of, what a meteorite composition is to find out what they might have been looking at that wasn't original material,
I did not think of that if I'm being completely honest, because I guess I've been doing this research for the last semester in the summer, and it has been pretty short. I've always been interested in astrobiology, but to be able to go in that depth and understanding, but that is a really interesting thing, and when I go home I'm going to do my own research on that, because I didn't think of it that way. Yeah.
Well, that was my question. Anyway, with the equipment that you have and people in this field, if you had a piece of Mars or Venus or whatever, I guess what you're looking for is carbon-based life remains of some sort in there. Would you be able to recognize if there were a different type of life that we don't know? I mean, I don't want to say aliens, but they're people that breathe ozone and whatever, made of different things. Would you be able to detect a different type of life form in this?
See, that's a really interesting question, because that is one of the big astrobiology questions too, because at the end, how do you define life? Like, what technically is something that's living? And to be able to define biogeneticity, which basically means if something was formed because of biology, is a question that you don't know how space is going to react to, and like what sort of different things and different chemical compositions are out there. But I guess my thinking is if something like that does happen, it's going to leave behind a trace that we are not familiar with. And I feel like a question mark is better than definitely it being a defined answer that no, that was not formed because of life. So that's why ambiguous signatures exist. That means we have not been able to classify them as life or as not life.
Aliens. Oh.
You know what, maybe. Microwave aliens, who knows?
I think this breaks down to two questions. In the lab, you're using lasers to excite the samples. Is this a technique you're able to use on remote objects in space that you can't hit with a laser, or only things that you can hit with a laser?
I do know that Raman spectrometry has happened in a larger scale in terms of satellite imaging and spectrometry in general. And I have still not had my hands on enough data to understand how that works. But I do think it is possible. I just don't remember how right now.
Okay. And the other question, you're using fairly narrow frequency ranges of lasers, and I see your results cover a wide frequency range. Is that because of the fluorescence covers a wide range, or how does that happen?
Okay, so generally, like if I'm talking about Sherlock, the Raman spectrometer on perseverance, it is using fluorescence too, and I'm going to check my notes because I know that I may have answered this somewhere. Yeah, it's using Raman and fluorescence together because it has two separate filters, but if it does over a larger range, the detections increase, and the image I showed you, it is not showing, but had different peaks, and they are very distinct when you think about them at a sort of chemical rock level when you need to find out the composition of a specific angle. That's why they are done at a broader range, is what my understanding is.
So, so the rock that you were studying, that you showed us, and you showed us the signature. So, what are the results for that now? Have you found? Does it seem like it's the same signature as what Sherlock or Watson have found on Mars, or?
That's what I'm studying next semester. I've applied for the funding already.
Okay.
I actually just submitted my application
Right.
for
So
the
you've got this
undergrad.
one, right? So you've got this signature, and then if you can get that data, you're going to compare.
I am actually planning on increasing my data sample size,
Okay.
like looking at different marine environment rocks and different
Oh, okay.
rocks that are formed and being able to compare all of them and having them as like a set
Right,
to then compare because
right. To see what
To
kind of
be honest-
variation you've got. and,
yeah, exactly, because you can't expect that the whole planet to be analyzed as quickly as Sherlock has just gone there. We have a good number of samples, like that has been done on Sherlock, but we don't know if they all have been done like in relation to, like there may be a big ocean, and has Sherlock only covered that part of the craters where the ocean was, and so I feel like having a larger database and sample size is going to give me enough variation to be like, okay, if this has life, that has life, how may we be able to see them compared to all of these to the kind of base fits I'm going to get with Perseverance's Sherlock data.
Right.
And
Right.
that's my plan to do as I graduate as a senior, to go and research more on this and more on the astrobiology stuff. Because not gonna lie, this takes a lot of time.
And you'd like to get as close a signature to match the Martian signatures as possible.
Yep. And different kind of marine, like different environments like marine, submarine, caves, basins, anything that's low light, redox, low energy environment is something I want to look at. And that's why I'm trying to collect different rocks from different places. Cut a thin slice, put them under Raman, collect data, do base fittings, and see what is consistent in all and do a comparative analysis of that, plus the Perseverance data.
Right.
Anybody else?
Cool.
Well, thank you.
Yeah, thank you so much.
Let us know what you find.
I will.
Maybe next year or the year after that, you could come in and do a follow-up and let us know how the research
My
is going.
plan, because I today sent out my application for an undergrad research award that KU has, and I feel like the next semester and winter is when I'm going to increase my sample size and combine all that research and get it ready so that my last whole year can be a comparison done. Oh yeah.
Are you planning on going on doing graduate work in this area?
I wish. I am kind of scared I'm not smart enough. I'm gonna say no. Because I'm not a good student, I'm a good researcher and a scientist, but I'm a terrible student. So I'm working on that. Maybe, I hope I get in.
Yeah.
But it's also a matter of how much it's going to cost me. But I hope so.
Thank you for coming out this evening.
Yeah, it's very interesting.
Thank you.
Thank you.